So in the warm-up, we discussed that students can often develop an intuitive understanding of irrational numbers through estimation. So for example, if we wanted to approximate the square root of 12, then students might think, okay, well, that's not a perfect square, but it is in between the two perfect squares of 9 and 16, right? 12 is in between 9 and 16. Here's 12 in the middle. And so it would make sense that the square root of 12 should be in between the square root of 9 and the square root of 16, which means the square root of 12 is somewhere in between 3 and 4. Okay, and so students might not understand then how to improve those approximations. Like, is the square root of 12 3.5-ish, right? How do we know how to improve that approximation? A teacher could just say, okay, well, try 3.4 squared, try 3.5 squared, see if 12 is in between those two numbers. But, right, why do we try those specific decimals, right? And does this method necessarily guarantee that we're going to find success? So analysis kind of gives us some tools to help understand the answers to those. Now, when we're doing these approximations, we're not actually producing an approximation so much as we're producing bounds, right? So we found that the square root of 12 was in between 3 and 4. It's greater than 3, but it's less than 4. And that's giving us a bound, right? So this is sort of our bound, our lower bound A and our upper bound B in this example. So if x is any real number, we define an upper bound, D, to be, or for a number x, to be a real number that is greater than x. Well, greater than or equal to x, or equal to. And so really, an upper bound for x is just some number d that's greater than or equal to x. Similarly, a lower bound c for a number x is just any real number c that's less than or equal to x. Less than or equal to x, right? So we have that c is less than or equal to x, and putting those together gives us our bounding interval. So it's a closed interval. So it's a set of all real numbers between c and d such that x is in that interval. So c is less than or equal to x, which is less than or equal to d. And an approximation is really just any real number that's used to approximate x. So we write x sub APPR, x sub approximation, to be any real number approximating x. Might not be a good approximation, right? Like if I was trying to find the square root of 150. No, that's maybe not a good example. Right? You might have a poor approximation. So any approximation, right? Any real number that you're using to approximate x is what we're calling our approximation. But it's helpful for us to describe how good of an approximation it is using something called an error. So if we're given a real number a and we're giving some approximation a sub APPR, a sub approximation, the actual error is just going to be how far off you are. So it's really just going to be the absolute value of a, the real number, minus the approximation of a. But the potential error, or the error bound, is going to be the known, or a known, maximum value that the actual error could be. So I'm going to give you an example of that in a second. So it's a positive real number, which we'll call e, such that the potential error is some positive real number e. I'm just going to say e is an element of R plus because it's a positive real number, such that the interval between the approximation minus the error bound, and then the approximation plus the error bound is going to be a bounding interval for A. In other words, A is guaranteed to be in that interval. And that means that the absolute value of A minus A, the approximation, is less than E. Okay, and so to give you an example of that, let's say our real number A, choose a different color here, let's say our real number A is pi, but we're using the approximation, as we often do, of 3.14. Then the actual error here is going to be pi minus 3.14. So it's going to be something like 0.001592, blah, 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 blah. But the error bound, we know that number pi is going to be somewhere between 3.14 and 3.15, right? And so since pi is in the interval between 3.14 and 3.15, that gives us an error bound, right? It's telling us you're going to guarantee to be in that interval. And so this allows us to say things like our approximation is going to be accurate within, 0.01 or whatever it is. So let's look at another example. If we had some kind of a method, and we haven't really defined it carefully yet, but if we had some method to generate better and better approximations of an irrational number, like an irrational root, like square root of 12, this is going to yield a sequence. So for instance, if we were trying to approximate the square root of 12, and we use the following sequence, 3, 3.4, 3.46, 3.464, we're getting closer and closer to the square root of 12. But really what we're doing is we're narrowing down the interval that contains the square root of 12 by checking the squares of tenths, hundredths, and so on, right? We can narrow down from 3 to 3.4 by computing 3.4 squared, 3.5 squared, and seeing that the square root of 12 is in between there, right? From there, we can compute 3.46 squared, 3.47 squared, and see that the square root of 12 has to be somewhere between there, okay? And so each term really is going to be the left endpoint of an interval containing the square root of 12. So, each term in our sequence is the left endpoint of an interval that's guaranteed to contain the square root of 12. Like for instance, 3 is in the interval from 3 to 4. It is, but that's not what I meant. Square root of 12 is in the interval between 3 and 4. So the left endpoint is our first term here. Then we narrow it down and say, actually, the square root of 12 is in the interval between 3.4 and 3.5. So that's the next left endpoint is the next element in our sequence. Then we can say, narrow it down even further and say the square root of 12 is in the interval between 3.46 and 3.47. Right? And each time really what we're doing is we're just checking to see that 3.46 squared is less than 12, but 3.47 squared is greater than 12. Right? And similarly for the steps before, similarly for the steps after. So that sequence that's approximating the square root of 12 is really just the left endpoints of each of these bounding intervals. And in this case, the error bound is just going to be the length of the interval, which is going to be shrinking by a power of 10 or by a factor of 10 at each step, right? So the length of our first interval is 0.1. Oh, actually, the length of our first interval is 1, I should say. The length of our second interval is 0.1. The length of our third interval is 0.01, and so on. So it's shrinking by a factor of 10 each time. And so the approximation A sub n has a consistent error bound of the form 1 over 10 to the n. Or I guess maybe it's 1 over 10 to the n minus 1, right? Since our first term, our a sub 1 term, really has an error bound of 1. But after that, it should work. Yeah. Okay. So what does this mean, right? How does this actually kind of help us to find these? Oh, we already talked about that. Well, if we actually want to try to figure out like how to find this sequence of rational numbers that's approximating our square root of 12, you could just sort of guess and check your way through. Like, let's say we're trying to approximate the square root of 12, and we're using a sequence, and we started with 3, and then we got to 3.4, and now we want to know what's next. 3.4 what? Well, you could kind of start at the beginning. Like, you could compute 3.41 squared, 3.42 squared, 3.43 squared, and so on, until you find a number that's greater than 12. And then you can say, okay, now I found my interval. Now I know that it's between 3.46 and 3.47. But that's maybe not computationally the best way to do it. So we use something called a midpoint of recurrent interval to get just a better or a less computationally heavy way of doing this. So it might make sense to say, all right, I know that my square root of 12 is somewhere between 3.4 and 3.5. I'm going to start in the middle. I'm going to compute 3.45 squared. And I'm going to see, is it less than or equal to 12 when I square it? Okay, it's less than 12. So then I'm going to check 3.46 squared, and then I'll check 3.47 squared, and so on. So it just gives us a less computationally heavy way to figure out what the next one is. Of course, once we do that, we eventually see that 3.46 squared is less than 12, but 3.47 squared is bigger than 12, which means the next approximation in our sequence is 3.46. Right, and then we sort of continue from there. Our next step would be, I want to figure out what the next decimal point should be, so I'm going to try 3.465 squared and see is it bigger than 12 or less than 12, and so on. All right. Now, the question is, does this actually converge? If we use this method to come up with a sequence of approximations, do we know that that's going to converge to the square root of 12? How do we know? Well, we really need some formal definitions to help us here, and this is where the tools of analysis are important. We want to define convergence in order to formalize the idea that our sequence is getting arbitrarily close to that square root of 12 that we're looking for. The way that we define this is we say that a sequence of real numbers, a sub n, converges to a real number a if for every epsilon greater than 0, there exists a natural number n, we'll call it capital N in the set of natural numbers, such that whenever little n is greater than or equal to capital N, we have that the absolute value of an minus a, in other words, the distance between the number we're approximating and that a sub n is less than epsilon. So I'm using this right arrow to make an if-then statement, right? If n is greater than or equal to n, then the distance between an and a is less than epsilon. All right, so really here, think of epsilon as being a teeny tiny number, right? Something very, very small. This epsilon represents how close we want to be to that limit, how good we want our approximation to be. The existence of such an n, such a big N, guarantees that beyond some point, all terms in the sequence are going to lie within epsilon of our chosen values. So let me just try to draw a quick picture. Let's say we're trying to approximate the square root of 12. I know it's between 3 and 4 somewhere. Right, square root of 12. And I have this sequence of values that's hopefully getting closer and closer and closer, right? So this is our A1, our first approximation, our A2 is our second approximation, and so on. Then what this definition is saying is that I can choose a teeny tiny value of epsilon, maybe something as small as like 0.0001. And this says that I can find an index, an a sub something, so that all of my values of my sequence are within 0.001 of my target number square root of 12, right, of my a. So if epsilon is equal to 0.001, I want to say there has to be some index n such that every other element of my sequence is within this target window. It's within 0.001 of the square root of 12. And we'll see in the exercises that we can use this to show that this is actually going to work. And why does this matter? Well, if we know that our error bound at step n is less than epsilon, and if our approximations are always going to be within the bound after that point, then we can conclude that yes, this sequence is converging to the real number that we're trying to approximate. And, we can use a calculator to approximate the square root of 12, but really, how is the calculator doing that? They're doing this exact thing. They're doing this exact method. They're doing it quicker than us, but they're using the same idea. And we really need the ideas of analysis to convince ourselves that this method is actually going to give us the correct approximation. It's actually going to get us as close as we want to the square root of 12.